The winter of 1891 hit northern Minnesota's logging camps hard. John Anderson watched his neighbor's cabin drop to 15 degrees Fahrenheit, despite feeding the cast iron stove every 3 hours, burning through 4 cords of seasoned logs in just 3 weeks before the water pipes froze and burst. Anderson had built his heating system exactly like every other homesteader in the timber country was told to build it. Standard wood stove, seasoned logs only, frequent feeding day and night, proven and trusted. Across the logging frontier, settlers were burning through their winter wood supplies faster than they could haul it, fighting the same losing battle against sub-zero cold. The logging camp foreman called Anderson's new contraption a junk barrel heater when he quietly began packing sawmill waste into a metal drum around a central air tunnel. That packed sawdust smoldered hot for 24 hours straight on a single lighting, heating his cabin through a minus 30-degree night while using 30 pounds of waste instead of half a cord of logs. In this video, I'll break down the exact packing method, the airflow design, and the 3 principles behind this forgotten frontier heating system. What did Anderson understand about slow burn combustion that every other settler in those frozen woods had missed? The sawdust had burned through the night, but John Anderson woke that February morning in 1892 to a community that refused to believe what they had witnessed. The logging camp foreman, Buck Mason, stood in Anderson's doorway, examining the warm cabin interior, while his own crew quarters remained barely above freezing despite feeding their standard cast iron stoves every 4 hours. Mason ran his hand along the metal drum that still radiated heat from its stone base, then shook his head and muttered that any contraption burning mill waste would fail when the real cold hit. The other homesteaders gathering outside Anderson's cabin that morning carried the same skepticism, insisting that seasoned cordwood remained the only reliable fuel for Minnesota winters that routinely dropped to minus 30 degrees Fahrenheit. Anderson had arrived in the timber country from Dakota Territory 3 years earlier, carrying 40 years of carpentry and blacksmithing knowledge gained since emigrating from Sweden in 1849. His weathered hands knew the feel of quality ironwork, and his memory held clear images of the Kakaloon tile stoves from his childhood village near Göteborg, massive masonry heaters that his grandfather fed once each morning to warm the house through long Nordic nights. Those Swedish stoves operated on principles that American frontier settlers had abandoned: store heat in thermal mass, burn fuel slowly rather than fast, and eliminate the constant tending that exhausted families through winter months. But the Kakaloon required skilled masons and imported firebrick, resources unavailable in northern Minnesota's remote logging camps, where men built from available materials or froze. The breakthrough had come during his second winter in the region, when Anderson spent 3 days at an Ojibwe hunting camp 40 miles north of the logging operation. An elder named Misquabic Bear had shown him how lodge builders packed cedar bark bundles around a central wooden stick, creating a hollow column that burned steadily from the inside, while the packed outer bark smoldered slowly for hours. The technique required precise moisture content in the bark and careful tamping to achieve the right density, knowledge passed down through generations of winter camp construction. Anderson watched Bear's Lodge maintain comfortable temperatures through a 2-day blizzard using only small amounts of cedar waste that other builders would have dismissed as worthless scraps. The Swedish masonry principles and Ojibwe packing methods converged in Anderson's mind during a failed experiment that spring. He had attempted to create a quick-warming fire using bundled wood shavings from the sawmill, hoping to reduce the labor of splitting seasoned logs. The shavings ignited in a spectacular flame that heated his workshop rapidly, then collapsed into cold ashes within 30 minutes, leaving him colder than when he started. The failure taught him that surface area and air supply determined burn rate more than fuel quantity, and that controlling combustion required managing both the fuel arrangement and the oxygen flow. Through the summer of 1891, Anderson quietly gathered materials and refined his design concept. The sawmill produced enormous quantities of waste sawdust, shavings, and bark strips that accumulated in piles behind the cutting sheds, material that mill operators paid workers to haul away and dump in distant clearings. Anderson secured permission to collect this waste, claiming he needed it for workshop floor covering, while actually testing moisture content and burn characteristics in small experimental fires. He discovered that sawdust, with approximately 12% moisture content packed to a density of roughly 1 pound per cubic foot, would smolder steadily rather than flame or collapse when ignited from below through a central air channel. The 30-gallon metal drum came from a failed whiskey operation that had left behind several large containers suitable for conversion. Anderson's blacksmithing skills enabled him to cut precise vent holes and fabricate the removable dowel system that would create the central air tunnel. He calculated that 30 pounds of properly packed sawdust around a 2-inch diameter central channel would provide sufficient fuel mass for sustained combustion while allowing adequate airflow to maintain the smolder throughout a winter night. The drum's iron walls would conduct heat efficiently into the cabin space, while the planned stone base would provide thermal mass to moderate temperature. Swings. Mason and the other homesteaders remained unconvinced despite witnessing the successful 24-hour burn. They argued that mill waste contained moisture, bark fragments, and debris that would create dangerous creosote buildup in chimney pipes, a legitimate concern given the cabin fires that claimed several structures each winter in the logging region. Traditional wisdom insisted that only seasoned hardwood logs, split to proper dimensions and dried for at least 1 full year, provided safe and reliable fuel for cast iron stoves. The established method required cutting 3 full cords of wood for each winter month, splitting the logs to forearm thickness, and maintaining sufficient seasoned inventory to prevent dangerous shortcuts during cold snaps. Anderson acknowledged these concerns while pointing out the labor and resource costs of the conventional approach. Each cord of seasoned wood required approximately 16 man-hours of cutting, splitting, and hauling, meaning that a typical winter demanded 48 cords and nearly 800 hours of wood preparation labor. Homesteaders often exhausted their wood supplies during extended cold periods, forcing them to burn green wood that produced poor heat and dangerous creosote, or to purchase emergency cord loads at premium prices that strained household budgets beyond sustainability. The packed sawdust approach promised to eliminate both the labor-intensive preparation and the supply vulnerability that plagued log-fed heating systems. Sawmill waste cost nothing beyond the labor of collection, required no splitting or seasoning time, and remained available throughout the winter as long as the mill operated. The controlled burn technique would theoretically produce more complete combustion than the erratic flame patterns of conventional log fires, reducing creosote formation while extending heat output per pound of fuel consumed. But theory required validation through the harsh testing ground of a Minnesota winter, and Anderson understood that his neighbors would demand proof beyond a single successful night. The logging camp community operated on practical demonstration rather than theoretical arguments, and any heating innovation would need to survive multiple freeze-thaw cycles, supply disruptions, and the inevitable equipment failures that challenged all frontier technology. Mason had already warned that the packed sawdust system would fail when tested by sustained sub-zero temperatures, equipment malfunctions, or fuel supply problems that revealed the superiority of traditional methods. Anderson spent the remaining weeks of that winter documenting temperatures, fuel consumption, and maintenance requirements for both his experimental system and the conventional stoves operated by his neighbors. The data would provide the foundation for convincing skeptics that traditional knowledge, properly adapted to frontier conditions, could outperform the accepted wisdom that trapped homesteaders in cycles of excessive labor and resource consumption. The crisis struck Anderson's neighbor in January of 1891 when an ice storm followed by 3 weeks of sub-zero temperatures exposed the fatal weakness of conventional log-fed heating. Thomas McKiernan had stockpiled what he calculated as sufficient seasoned oak and maple for the winter months, but the sustained cold forced him to feed his cast iron stove every 2 hours instead of the normal 4-hour intervals. By mid-January, his seasoned wood supply was exhausted, forcing him to burn green logs and bark waste that produced spectacular flames but little sustained heat. The wet wood created thick creosote deposits that clogged his chimney pipe, reducing draft and filling his cabin with smoke. Despite burning through 4 full cords in 3 weeks, his cabin interior dropped to 20 degrees Fahrenheit during the coldest nights, and McKiernan faced the expensive reality of purchasing replacement wood at $40 per cord while losing 2 full days of labor hauling emergency fuel through deep snow. Anderson recognized this failure as the perfect opportunity to validate his packed sawdust combustion theory under genuine frontier conditions. The key insight came from his conversation the previous summer with Chief Little Whip, an Ojibwe hunter he had encountered during a supply run to the northern camps. Little Whip had demonstrated how his people created long-burning heating systems by packing cedar bark bundles around a hollow central stick, then removing the stick to create an air channel that fed oxygen to the fuel mass from the bottom while limiting the burn rate through controlled packing density. The technique produced steady heat for 8 to 10 hours from materials that conventional fire building would consume in 30 minutes. The Swedish connection reinforced this indigenous knowledge through Andersson's memories of village craftsmen near Göteborg who built kakelun masonry heaters based on the principle of fire once, heat many hours. These Swedish builders understood that rapid combustion wasted fuel by sending most of the heat energy up the chimney, while slow, controlled burning transferred more thermal energy to the surrounding space. The challenge lay in adapting these old-world masonry techniques to frontier conditions using available materials and simple construction methods that homesteaders could replicate without specialized training. Andersson's preliminary testing in the spring of 1890 had confirmed the basic feasibility of sawdust fuel when properly prepared and packed. He had filled a 5-gallon pail with sawmill waste, tamped it around a 1-inch wooden dowel to create uniform density, then removed the dowel and ignited the fuel column from the bottom opening. The test burn lasted 2 hours with steady heat output, proving that sawdust could sustain combustion when airflow was restricted to the central channel rather than allowed to penetrate the entire fuel mass. The experiment also revealed the critical importance of moisture content and packing pressure in achieving successful smoldering rather than rapid surface burning or collapse. The technical breakthrough required solving 3 interconnected combustion problems simultaneously. First, the sawdust moisture content needed precise calibration because excessive dryness caused rapid flaming, while excessive moisture prevented ignition or produced choking smoke. Andersson developed a simple hand squeeze test where properly conditioned sawdust would hold its shape when compressed but crumble when disturbed, indicating approximately 12% moisture content. Second, the packing density determined whether the fuel would burn steadily or collapse into uneven hot spots and cold zones. Through repeated trials, he established that tamping the sawdust to approximately 1 pound per cubic foot created optimal burn characteristics. Third, the central air channel diameter and the bottom ventilation opening size controlled the combustion rate and prevented both oxygen starvation and excessive draft that would consume fuel too rapidly. The full-scale implementation began in September of 1891 when Andersson loaded his 30-gallon conversion drum with precisely measured materials. He packed 30 pounds of conditioned sawdust around a 2-inch diameter wooden dowel, tamping each layer to maintain consistent density throughout the 2-foot height of the fuel column. The dowel removal required careful technique to preserve the smooth-walled air channel that would function as the combustion system's chimney, drawing oxygen from the bottom vent opening and distributing it evenly through the packed fuel mass. A 1/4-inch steel plate welded over the drum's original opening provided the controlled bottom vent, while a standard stovepipe connection allowed exhaust gases to exit through his existing chimney system. The ignition process demanded precision timing and placement to establish the slow burn pattern correctly. Andersson inserted wood shavings and birch bark tinder into the bottom of the central air channel, then lit the kindling while the bottom vent remained fully open to establish initial draft. As the kindling burned upward into the packed sawdust, he gradually reduced the bottom vent opening to limit airflow and transitioned from rapid flame to controlled smolder. The critical moment occurred when the surface flames disappeared and the fuel mass began glowing internally, indicating that combustion had shifted to the desired slow burn pattern. The results exceeded even Andersson's expectations based on his Swedish childhood memories. After 22 hours of continuous operation, the drum's exterior surface temperature measured approximately 200 degrees Fahrenheit when tested with water drops that sizzled instantly upon contact. The cabin interior had risen from 45 degrees Fahrenheit at ignition to 75 degrees Fahrenheit and maintained that temperature throughout a night when outdoor temperatures dropped to -10 degrees Fahrenheit. Most significantly, the fuel consumption represented a dramatic efficiency improvement. 30 pounds of waste sawdust had provided the same heating duration that would normally require half a cord of seasoned logs, weighing approximately 1,000 pounds. The controlled combustion process produced remarkably clean burning compared to conventional log fires. The restricted air supply and uniform fuel distribution created complete combustion with minimal smoke production and virtually no creosote formation in the chimney pipe. This clean burning resulted from the sawdust's small particle size and consistent moisture content, which allowed more thorough fuel consumption than the irregular burning patterns of split logs that created alternating hot and cool zones within standard fireboxes. Anderson's documentation of fuel consumption, labor requirements, and temperature maintenance provided quantifiable evidence that challenged fundamental assumptions about frontier heating economics. The labor investment for a single ignition totaled less than 30 minutes compared to the multiple daily feedings required by log-fed stoves. The fuel cost remained essentially zero since sawmill operators paid to have the waste removed, while the heating output matched or exceeded that of premium seasoned cordwood. Most importantly, the system eliminated the constant vigilance and overnight tending that exhausted homesteading families throughout the brutal Minnesota winter months. This technical validation prepared Anderson to address the remaining skepticism from neighbors who insisted that no heating system could function reliably without seasoned hardwood fuel and frequent human attention. The packed sawdust combustion method had proven its basic effectiveness, but frontier acceptance required demonstration under the most challenging conditions that winter could deliver. The success of the packed sawdust combustion system revealed a deeper problem that winter of 1892. Anderson's cabin envelope bled heat so rapidly that even his efficient fuel source required feeding every 3 hours to maintain livable temperatures. Despite the drum's steady output, the interior temperature dropped from a comfortable 70 degrees Fahrenheit at bedtime to 50 degrees by dawn, when outside temperatures reached minus 20 degrees Fahrenheit. The single sawn board walls, chinks between the original log construction, and gaps around the door frame created thermal hemorrhaging that undermined the fuel efficiency gains he had achieved. 3 cords of sawdust per winter month still represented progress over conventional log consumption, but Anderson recognized that heat retention demanded systematic envelope improvements beyond simply perfecting the combustion. Source: the solution emerged through an encounter with Heinrich Müller, a German-Swiss immigrant carpenter who had arrived in the logging region that fall, carrying knowledge of Black Forest building techniques adapted for severe mountain winters. Müller had spent his apprenticeship years in villages where temperatures routinely dropped to minus 25 degrees Fahrenheit and wood remained scarce and expensive, forcing builders to maximize every unit of heat energy through sophisticated envelope design. He observed Anderson's cabin during a November cold snap and immediately identified the thermal bridging through the log wall structure and the convective losses around unsealed openings that were bleeding interior warmth into the frigid outdoor environment. Müller's diagnostic method revealed heat loss patterns invisible to conventional frontier building practice. He dampened his hand and moved it systematically around the cabin's interior perimeter, feeling for air currents that indicated infiltration points where cold outdoor air penetrated the building envelope. The gaps between logs, despite being chinked with mud and moss, allowed continuous air exchange that carried away heated interior air and replaced it with cold outdoor air. The single-board siding provided minimal insulation value, creating thermal bridging where heat conducted directly through the wood structure to the exterior. Most critically, the door opening lacked any buffer zone to prevent cold air from rushing into the heated space each time someone entered or exited the cabin. The straw bale insulation technique addressed the conductive heat loss through a method Müller had learned from alpine builders who faced similar challenges of scarce fuel and extreme cold. The installation required dismantling sections of the exterior siding to expose the log wall structure, then packing 6-inch thick layers of straw bales between the logs and replacement siding boards. The straw's cellular structure trapped air in thousands of tiny pockets, creating an insulation barrier with thermal resistance approximately 4 times greater than solid wood. Müller demonstrated the proper straw preparation technique, cutting bales into uniform sections, soaking them briefly in lime water to prevent rodent infestation, then compressing each section to exactly 6 inches thickness before installation between vertical furring strips. The construction process demanded precise attention to moisture management and structural integrity. Each straw section required protection from rain and snow during installation through temporary canvas coverings, while strategic gaps allowed air circulation to prevent moisture accumulation that could lead to rot or mold formation. Miller showed Anderson how to create vapor barriers using pine pitch and linseed oil applied to the interior log surfaces, preventing warm, humid interior air from condensing within the insulation cavity. The exterior siding. Reinstallation included overlap joints and proper drainage details to shed rain and snowmelt away from the insulation layers. The vestibule design drew from Misquabic Bear's detailed explanation of Ojibwe Winter Lodge construction, specifically the double entry system that eliminated the thermal shock of direct exterior access. Bear had visited Anderson's worksite during the envelope improvements and demonstrated how his people created airlock chambers using overlapping hide flaps that prevented cold outdoor air from rushing into heated interior spaces. The principle required creating a small intermediate chamber where entering persons could pause, allowing the outer door to close completely before opening the inner door to the main living space. Anderson's vestibule construction adapted this indigenous technique to frontier carpentry methods using available lumber and hardware. The outer chamber measured 4 feet by 6 feet, large enough for one person to enter completely while carrying armloads of firewood or supplies. The outer door opened outward to prevent snow accumulation from blocking egress, while the inner door opened inward to create positive pressure that helped seal the airlock when both doors were closed. A simple knockboard provided a place to remove snow and ice from boots before entering the main cabin, preventing moisture infiltration that could compromise the interior thermal environment. The masonry thermal mass installation represented the most technically challenging envelope improvement, requiring Anderson to apply his blacksmithing knowledge to stone and mortar work. The existing drum installation sat directly on the wooden floor, radiating heat rapidly into the cabin air, but lacking any thermal storage capacity to moderate temperature swings. Mueller explained the Alpine principle of spiker mass, thermal storage systems that absorbed heat energy during peak combustion periods and released it gradually over extended time periods, smoothing the temperature curve and reducing fuel consumption. The stone-based construction required excavating a 4-foot square foundation pit 18 inches deep, then building up layers of field stone and fire-resistant mortar to create a raised platform 4 inches above the cabin floor level. The platform's thermal mass weighed approximately 800 pounds when completed, providing substantial heat storage capacity that would absorb energy from the drum during active combustion and continue radiating warmth for hours after the fuel was consumed. The 6-inch thick brick walls surrounding 3 sides of the drum created additional thermal mass while directing radiant heat toward the cabin interior, rather than allowing it to escape through the exterior wall. The mortar recipe combined local clay, sand, and crushed limestone in proportions Mueller had learned from Alpine masons who built heating systems designed to withstand repeated thermal cycling without cracking or structural failure. The mixture included chopped straw fibers to provide tensile strength and prevent shrinkage cracks, while a small amount of pine pitch added water resistance and flexibility. Each mortar joint required careful attention to eliminate air gaps that would compromise the thermal mass effectiveness and create weak points where repeated heating and cooling could cause structural damage. The integration of insulation, vestibule, and thermal mass created a systematic envelope approach that addressed the 3 primary modes of heat loss: conduction through walls, convection through air infiltration, and radiation through thermal bridging. The winter testing of 1893 validated the combined system's effectiveness when outside temperatures reached minus 25 degrees Fahrenheit during a sustained cold period. Anderson's improved cabin maintained interior temperatures between 68 and 70 degrees Fahrenheit for 48 consecutive hours using a single sawdust loading, while his neighbor's unimproved cabin required constant log feeding and still experienced interior temperatures dropping to 45 degrees Fahrenheit. The quantified performance improvement demonstrated the multiplicative effect of combining efficient combustion with effective heat retention. The fuel requirement dropped to 30 pounds of sawdust for the 48-hour period, compared to his neighbor's consumption of approximately 1 full cord of seasoned logs weighing nearly 2,000 pounds. The labor reduction eliminated overnight tending entirely, allowing uninterrupted sleep during the coldest periods when conventional heating systems demanded constant attention. Most significantly, the envelope improvements had transformed the Sawdust combustion system from an efficient heat source into a complete thermal management solution that addressed every aspect of frontier cabin heating. The spring thaw of 1894 exposed a critical vulnerability in Anderson's heating system when snow melt and ice formation blocked the air intake pathways that fed his drum combustion chamber. What had been a reliable 22-hour burn duration collapsed to barely 8 hours of effective heating as the packed sawdust smoldered unevenly and eventually extinguished itself when oxygen supply became inadequate. The failure occurred during a late March storm that deposited heavy wet snow followed by a hard freeze, creating ice dams that sealed the bottom vent opening and reduced the central air tunnel's effectiveness to the point where combustion could not sustain itself through the night. Meanwhile, his neighbor Thomas McKiernan faced even worse problems with his conventional cast iron stove when shifting wind patterns created backdrafting that filled his cabin with smoke and forced him to extinguish his fire entirely during the storm. The solution required understanding the relationship between combustion air supply and draft, control, knowledge that came through Anderson's encounter with Franz Keller, an Austrian immigrant who had arrived in the region that winter carrying expertise in alpine stuba construction. Keller had observed Anderson's system during a supply run and immediately recognized the draft management problems that plagued most frontier heating installations. In the Austrian mountain villages where Keller had learned his trade, builders routinely installed dedicated outside air intake systems that fed combustion chambers directly from outdoors rather than drawing heated interior air into the fire, a technique that improved both fuel efficiency and indoor air quality while preventing the pressure imbalances that caused backdrafting and smoke infiltration. The outside air intake installation required precise engineering to function reliably under Minnesota's extreme weather conditions. Keller showed Anderson how to fabricate a 4-inch diameter sheet metal duct that connected the drum's bottom vent to an exterior air intake positioned 3 feet above ground level and protected by a weatherproof hood that prevented snow and rain infiltration. The duct ran beneath the cabin floor through a carefully sealed penetration that eliminated air leaks while allowing thermal expansion and contraction of the metal components. The exterior intake hood included an adjustable damper plate that could be positioned to control airflow volume while maintaining protection from weather and debris. The internal damper system addressed the need for precise combustion control under varying outdoor conditions and fuel loads. Keller demonstrated the quarter-turn damper mechanism he had learned from Austrian stuba builders, a simple but effective device installed within the stovepipe that allowed operators to throttle exhaust flow and thereby regulate the draft that pulled air through the fuel bed. The damper consisted of a circular steel plate mounted on a central shaft that could be rotated from fully open to nearly closed positions, with detent stops that provided repeatable settings for different operating conditions. An external handle and position indicator allowed adjustment without opening the system or exposing operators to heat and combustion gases. Misquabic Bear contributed additional refinements based on Ojibwe Lodge ventilation techniques that used adjustable openings to manage airflow patterns around central heating systems. Bear explained how his people created controllable air inlets using bark flaps and wooden slide covers that could be positioned to provide precise ventilation rates depending on wind direction, outside temperature, and desired interior heating levels. The principle involved creating multiple small openings rather than single large vents, allowing fine-tuned airflow management that prevented the sudden pressure changes that could extinguish low-intensity fires or create dangerous backdraft conditions. Anderson adapted this indigenous knowledge by installing a 6-inch square adjustable vent plate directly above the drum's central air tunnel, creating a secondary air control point that worked in conjunction with the external intake damper and internal exhaust damper. The vent plate could be slid to various positions from fully open to nearly closed, providing immediate combustion rate adjustment without requiring access to the external or internal damper mechanisms. This 3-point air control system allowed precise management of the combustion process under changing weather conditions while maintaining the safety and simplicity that frontier operators required. The draft control system also incorporated temperature monitoring capabilities that helped operators optimize performance without guesswork or dangerous experimentation. Anderson fabricated a simple embedded thermometer using an iron rod inserted through the drum wall into the fuel bed, with the external end serving as a temperature indicator that showed the internal combustion intensity. When the rod became too hot to touch comfortably, the burn rate was excessive and required damper adjustment to reduce airflow. When the rod remained cool enough for extended hand contact, insufficient combustion indicated the need for increased air supply through damper opening or vent adjustment. The integrated air management system underwent rigorous testing during the winter of 1894, when sustained windstorms and deep snow accumulation created the most challenging draft conditions Anderson had yet encountered. Wind gusts reached 40 miles per hour, while snow depth accumulated to 12 inches, conditions that had historically caused heating system failures throughout the logging region as chimneys became blocked, air intakes sealed with ice, and draft patterns disrupted by shifting weather fronts. Anderson configured his system with the external intake damper set to half-open position, the internal exhaust damper adjusted to 3/4 open, and the adjustable tunnel vent positioned to provide moderate airflow to the fuel bed. The controlled burn test lasted 27 hours despite the severe weather conditions, with interior temperatures maintained between 70 and 75 degrees Fahrenheit, while outside temperatures dropped to -15 degrees Fahrenheit with sustained wind exposure. The fuel consumption remained at approximately 30 pounds of packed sawdust, demonstrating that proper air management eliminated the fuel waste that resulted from uncontrolled combustion rates. Most significantly, the system required only the initial ignition procedure with no overnight tending or emergency interventions, despite weather conditions that forced neighboring homesteaders to maintain constant fire supervision and frequent fuel additions. McKiernan's experience with his conventional log-fed stove during the same storm provided dramatic comparison data that validated the importance of controlled air supply and draft management. His cast iron stove required feeding every 2 hours to maintain adequate heat output, consumed nearly half a cord of seasoned logs during the 27-hour period, and still allowed interior temperatures to drop to 60 degrees Fahrenheit by dawn, despite the constant attention and fuel consumption. The backdrafting problems during wind gusts forced him to partially close his chimney damper, which reduced heating efficiency and created dangerous carbon monoxide accumulation that required periodic cabin ventilation even during the coldest portions of the storm. The quantified performance comparison demonstrated that proper draft and ventilation control could eliminate both the fuel waste and safety hazards that plagued conventional frontier heating methods. Anderson's controlled air system had converted approximately 30 pounds of waste sawdust into 27 hours of consistent interior heating, while McKiernan's uncontrolled log system required nearly 2,000 pounds of premium fuel to achieve inferior temperature maintenance with significantly greater labor investment and safety risks. The technical integration of outside air supply, internal draft control, and adjustable ventilation created a comprehensive combustion management system that addressed every aspect of reliable operation under frontier conditions. The 3-point air control allowed operators to optimize performance for specific weather conditions, fuel characteristics, and heating requirements while maintaining the simplicity and safety that homesteading families demanded from their heating systems during Minnesota's brutal winter months. The winter of 1895 delivered the ultimate test when a massive Arctic air mass settled over northern Minnesota and remained stationary for 17 consecutive days, creating the most severe heating challenge the frontier region had experienced in recorded memory. Temperatures plunged to -35 degrees Fahrenheit and remained below zero throughout the entire period, while sustained winds averaged 20 miles per hour and deposited 22 inches of snow that drifted into massive banks against cabin walls and blocked access roads. The logging camp suspended operations when equipment froze solid, and supply wagons could not navigate the impassable trails, leaving homesteaders isolated with whatever fuel reserves they had stockpiled before the storm system arrived. The crisis exposed fundamental weaknesses in conventional heating strategies as neighbors throughout the region faced cascading system failures that threatened their survival. Thomas McKiernan's cast iron stove demanded feeding every 2 hours to maintain minimal interior warmth, but his seasoned log supply dwindled rapidly under the relentless demand for fuel. By the 8th day of sub-zero temperatures, McKiernan had exhausted his primary wood reserve and begun burning furniture, fence posts, and green timber cut from nearby trees that produce poor heat and dangerous creosote accumulation. His interior temperature dropped to 45 degrees Fahrenheit despite constant fire tending, and on the 12th day, his water pipes froze and burst, creating flooding that required emergency repairs in sub-zero conditions. Similar disasters struck homesteads throughout the timber region as the extended cold snap overwhelmed heating systems designed for typical winter conditions rather than extreme survival scenarios. The logging camp foreman, Buck Mason, reported that 5 cabins experienced frozen water lines, 3 suffered chimney fires from creosote buildup, and 2 families abandoned their homes entirely to seek shelter in the main camp building. Fuel consumption rates exceeded all previous records as desperate homesteaders burned through entire winter reserves in less than 3 weeks, creating shortages that forced emergency rationing and dangerous expeditions to cut replacement wood in life-threatening conditions. Anderson's integrated system faced the same brutal conditions, but responded with remarkable stability and efficiency that validated years of careful development and refinement. His comprehensive approach, combining packed sawdust combustion, envelope insulation, thermal mass storage, and precision air control, created synergistic effects that multiplied the effectiveness of each individual component. The thermal mass foundation absorbed and stored heat energy during peak combustion periods, then released it gradually to maintain consistent interior temperatures without continuous fuel feeding. The straw bale insulation prevented rapid heat loss through conductive pathways, while the vestibule airlock eliminated convective losses from door openings during the frequent trips outside required for snow removal and essential maintenance tasks. The system's performance during the 17-day ordeal demonstrated the transformative power of integrated traditional knowledge applied to frontier conditions. Anderson performed only 4 ignition cycles throughout the entire period, spacing them approximately every 4 1/4 days as the thermal mass and envelope retention extended burn durations far beyond the original 27-hour cycles, achieved during normal winter conditions. Each fuel loading consumed approximately 30 pounds of packed sawdust, bringing his total fuel consumption for the crisis period to 120 pounds of waste material that cost essentially nothing beyond collection labor. The air management system proved crucial during the extended test, as shifting wind patterns and snow accumulation created constantly changing draft conditions that would have destabilized less sophisticated installations. Anderson's 3-point control system allowed continuous optimization of combustion rates through adjustment of the external intake damper, internal exhaust damper, and tunnel vent opening to maintain steady burn characteristics regardless of external weather variations. The outside air supply prevented the pressure imbalances that caused backdrafting in conventional systems, while the temperature monitoring rod provided immediate feedback on internal combustion conditions that guided precise airflow adjustments. Interior temperature data collected throughout the crisis revealed the system's exceptional stability under extreme conditions. Anderson's cabin maintained a minimum temperature of 67 degrees Fahrenheit during the coldest nights, with average nighttime temperatures of 72 degrees Fahrenheit, despite outdoor conditions that challenged human survival limits. The thermal mass storage created temperature moderation that eliminated the dramatic swings between overheating and rapid cooling that plagued conventional heating systems, providing consistent comfort levels that allowed normal daily activities and uninterrupted sleep throughout the emergency period. The quantified performance comparison with conventional methods revealed the magnitude of Anderson's technical achievement. While neighboring homesteads consumed approximately 5 cords of wood, totaling 10,000 pounds of fuel, Anderson's system required only 120 pounds of sawdust waste to maintain superior interior conditions. The labor differential proved equally dramatic as neighbors invested approximately 8 man-days in emergency wood cutting, hauling, and constant fire tending, while Anderson's 4 ignition events and routine maintenance required less than 1 full day of labor throughout the 17-day period. Financial costs further emphasized the economic advantages of the integrated approach. McKiernan and other neighbors faced replacement expenses exceeding $200 each for burst water pipes, emergency fuel purchases, and structural repairs from overheated stoves and chimney fires. Anderson's system operated without failures or emergency interventions, requiring no additional investment beyond the initial construction materials and setup labor completed in previous years. The quiet vindication began immediately after the weather broke and normal travel resumed. Buck Mason led a group of neighboring homesteaders to Anderson's cabin, where they found warm, comfortable conditions and evidence of minimal fuel consumption, while their own homes remained cold and damaged despite heroic efforts to maintain heating. The skepticism that had persisted for 4 years evaporated as they examined the drum installation, thermal mass foundation, insulation details, and air control mechanisms that had enabled survival during conditions that had nearly killed them using conventional methods. Anderson shared his technical knowledge freely with neighbors who began constructing their own versions of the integrated system during the remaining weeks of winter. Sarah McKenna became the first successful adopter, building a simplified version using a 20-gallon drum and basic straw insulation that immediately reduced her fuel consumption by approximately 60%, while providing more consistent heating than her previous cast iron stove installation. Within 2 years, variations of Anderson's design appeared throughout the logging region as homesteaders adapted the principles to their specific situations and available materials. The technical legacy extended far beyond the immediate frontier community as agricultural extension agents documented the superior performance and included sawdust heating modules in official homesteading circulars published during the early 20th century. Thomas L. Green, an extension agent conducting field surveys 25 years later, reported finding dozens of surviving barrel stove installations that matched Anderson's original design geometry and performance specifications, evidence that the knowledge had spread throughout the upper Midwest frontier communities. Modern off-grid builders continue to reference the fundamental principles Anderson proved during that brutal winter: pack fuel for controlled combustion, insulate the envelope to retain heat, store thermal energy and mass for temperature stability, and manage air supply for optimal efficiency. These techniques validate the enduring wisdom of traditional knowledge systems that respond to real environmental constraints rather than theoretical assumptions, proving that careful observation and systematic refinement of established methods often outperform conventional approaches that ignore fundamental physical realities.